All right. So good afternoon. I hope everybody's weekend went okay. That nobody's having too much issues with the smoke. I have developed a slight cough, so don't be freaked out. It's not COVID, as far as I can tell. It's just the smoke. The thing we're going to talk about today is DC circuits. So we worked on the derivation of Maxwell's second law, and that came right at the finish line. Remember, we were talking about moving charges through an electric field, and then there was this scalar function associated with the electric field that we call the potential. And then when you move a charge through some kind of a arbitrary path, there's an associated potential difference with that. And that potential difference is independent of the path that you take, which means that if you take one path this way and then you go back in the other way, the potential change through that closed path is going to be zero. And that means that the line integral of the electric field through a closed circuit in an electric field is zero. So that's Maxwell II. So Maxwell II is not just using the relation that there's a relation between potential and electric field, but it also uses the fact that the electric field is a conservative field. Now, what was going on behind the scenes is we kind of quietly assumed that if we have some kind of a test particle and we let it go, it's going to gain kinetic energy, and that kinetic energy is not going to be converted to anything else, right? So the particle's moving through a completely frictionless medium, which obviously doesn't exist, but it's nice to start with a highly idealized world of spherical cows. So it moves through a medium without any friction. So that means that whatever energy is gained by letting that thing go and letting the electrostatic energy do its thing, it can all 100% be converted to kinetic energy. And similarly, if we have some kind of a particle that has a lot of kinetic energy, we shoot it towards that charge, it's going to bring that to a halt. If there's no other energies being lost or gained, that total energy difference is going to be exactly the opposite of the energy difference that we were using to get it to accelerate in the first place. So there was this conversion of potential to kinetic energy, and we said in that conversion, nothing else is lost, except in the ideal world of cars and swamps and resistors and friction, that's not really true. So we have to for DC circuits, we have to develop that idea a little bit further. So imagine, I don't like going to the mechanical analog, but imagine you have some kind of a car on a ramp, and the car is otherwise frictionless, and goes down the ramp and then comes up. Then that gain of kinetic energy that comes at the expense of potential energy comes down the ramp, go back up a ramp and go in a circle. And then in the end, if there's no friction, in the end, it'll have the same speed as it had when it started on the ramp, because the energy is conserved. Now, if there is some kind of friction, so for instance at the bottom of the ramp there's mud or something, so that introduces friction, that means it's going to lose some kinetic energy, so therefore it won't be able to make it back up the ramp again, and therefore it will, when it comes back, it will not be able to come back to its original position, because it will have lost some of that kinetic energy, and the kinetic energy will be converted into whatever it does when you drive through mud. I'm assuming some kind of a heat gets developed. So if the question is, we would like to have this car make a complete route through this, there at some point it's going to have to burn some gasoline to make up for the kinetic energy loss through the mud. So then the statement becomes, okay, if the car makes it back to its original position, whatever losses happened on the path must be exactly balanced by the gains, because it was burning some kinetic energy. So it's not a closed system anymore. So it's no longer about a single charge moving through a potential landscape, but it is about the fact that it needs to go in a closed path. And as long as you require it to go back to its original position, the gains and the losses need to be balanced. Otherwise, it can't make it. or it's going to gain energy and start accelerating like crazy. So that's the generalization that we will need, and we'll work on developing that, and we will do that now. All right. So we are continuing our journey into DC circuits. So to put in equations, the thing I was just telling you, well, we have this circuit integral of E dl, and that, if it's a closed path, so this is the contour around some kind of a surface, then that is 0, because the electric field is a conservative field. So that's Maxwell II. I believe circuital law, or Ampere circuital law. Later we will not only consider changes to this law due to the fact that we have power sources and losses, but we will also consider the effect of magnetic field. So this is not complete yet, but this will work for now. Okay, so I said, well, if there's some kind of a field, let me draw a field. There's some kind of a field, and it's a really weird field. Doesn't really matter how we got there. And if we take some kind of a closed path from, point A to point B to point C, point D, back to A again, so we can go in this direction. So this is point A to B to C to D. Then the total work done is 0. Potential energy gain is potential energy loss, or in other words, this line integral is 0. Or we can split this line integral. We can actually say, well, it's an integral from A to B of E dl plus an integral from B to C of E dl plus an integral, I'm being super verbose because I feel like it, E to D plus then back to where we started again. Okay, so D to A dl. Okay, now this voltage we called the delta V A to B, but we can also call it V A B, depending a little bit on your sign convention. Sometimes we'll do from A to B, we'll call it B to A, or it doesn't really matter. So we're going to call this VAB. We're going to call this VBC. We're going to call this VCD, and we're going to call this VDA. And the sum of all those voltages is 0. So rather than describing this as a bunch of line integrals, we can say sum of voltages is 0. All right. Now, to the example I was explaining. So I'm gonna get my demo. So I borrowed my kids' snap circuits. They're really, really cool to play with. All right. So this is an LED. It's a light, right? So batteries, light, wires to connect it to. So the world's most simple circuit. I just need to make sure to do it this way. LEDs are not the world's most simple resistor, but it helps because it's easy to power it up. So just assume it's some kind of a resistor. Okay, so there you go. So we have now a current path. So we have a bunch of batteries. There are 2 batteries in series. Forget about that for now. So it's just like what this diagram here says. There's some kind of a voltage increase, and that's the symbol for it. We'll go over all the symbols. There's a voltage increase, goes through here, and then there is light being generated, and then we go back here. So this light obviously radiates out into the universe, and we could capture it with a photocell, but other than that, it will be completely lost. So whatever energy is dissipated by it, I think it gets warm a little bit too if you're not careful. By it getting warm, that energy needs to be supplied by the batteries. So Therefore, if you take a test charge and you go from here through the battery, there will be some energy increase. And then from here through this light, there will be an energy decrease. And the total energy increase and energy decrease will add up to 0, because otherwise the particle doesn't make it all the way back. So in other words, before my batteries run out, even though LEDs don't take a lot of battery. So if we have some kind of a circuit diagram, so this, and this is my resistor. There's a power supply, some V. Sometimes we use the symbol E for that. And in this case, it's 3 volts. So it's 3 volts. And then this is a resistor. And now the circuital law generalized to the fact that there needs to be balancing of energy means that whatever potential increase happens here, because we have a battery here that's moving charges up and giving it a 3-volt boost, that energy needs to be dissipated here in this resistor. And the resistor, it becomes warm, so it radiates. And that energy lost, right? So that energy that is lost here because it gets warm, it comes from the battery, and the battery will get drained. But still, whatever potential increase happens here needs to be balanced by a potential decrease there. So here we go. That potential decrease there, that is V, is going to be I times R. And I here is the regular current, that's I. That is dq dt, as we have defined it before. We haven't really used it much. So this is the battery, gives it a 3-volt boost. There's a current that flows through the resistor. There's a 3-volt drop here, and then we're back here. So the voltage increase equal to the voltage decrease. So, so generalized from the form we had here, we can say the sum of all the voltages between points I and J, where J is I plus 1, is 0. So 1 voltage, 2 voltage, going up, going down. All right. So this is Ohm's law. I'm assuming you were all doing the 220B lab practical, so you've all seen Ohm's law before. And I apologize. Sometimes the labs, they are out of order with the lectures. This is not just the case for 226. It happens with 220B as well, and it's unavoidable because we're not really doing many electrostatics experiments. So in the lectures we have to do 2 or 3 weeks of calculus to develop Gauss's law, but we don't really use that in the lab. So in the lab, we just jump right in here, and this is where you start. So, but we finally are caught up. So hopefully you are familiar with this. This, of course, is the famous Ohm's law. So Ohm's law. Ohm's law says that if there's a resistor with a resistance R, then the units of R are in ohms, and we use the Greek omega, and we call that ohm or ohms. Then if there's a current flowing through that resistor, then the voltage drop is the current times R. All right, now here is an important caveat. V drops in the direction of the current. Okay, so well, let's see what that looks like. So I'm going to assign. So there's a point A, there's a point B, there's a point C, and then there's a point D. Let's assume that these are ideal wires, and nothing happens to the potential. Then, if I'm drawing the potential, as a function of position, we start off in point A. We're somewhere here. We go from A to B. We first have some wire, and then we go to B. And now we're at point B. So point B. And now we go from B to C. Nothing happens with the potential because it's a wire. And we assume it's an ideal wire. So end up in point C. Then we go from C to D. Now, the point where we go through this resistor is the point where we use Ohm's law. And as soon as we use Ohm's law, we need to check whether we're using this sign convention correctly. So in this case, the current goes in this direction. So therefore, it's a voltage drop in that direction. So that means voltage goes down. And now the question is, well, where does it go? Well, in the end, we have a straight shot to D and then to A. And between D and A, nothing can happen because it's a wire that is presumed ideal. So in other words, this drop here, there's nothing else to do. This drop needs to come out here because this law says so. So this is the voltage increase, that's E, and that's let's call it 3 volts. And this is a voltage drop. It's equal to R times I. We're not giving a sign to the current, it's just some number, but it is a voltage drop. So this 3 is equal to that, Ri. So we get I is V over R. In this case, E over R, because E and V are the same, because this increase is equal to that decrease. So we get 3 volts over the resistance. Now let's call this resistor. Let's call it 3 kilo ohms. So over 3 kilo ohm. So that gives you 1 milliamp. Done. All right. So that's Ohm's law. That's Ohm's law in action. We introduced a whole bunch of things. So this thing, it's called Kirchhoff's voltage law. Kirchhoff's voltage law. All right, so sum of all the voltages is 0. We've used Ohm's law. We also threw in, for good measure, a couple of symbols here. So we have the essential building blocks. We have a power supply. Could be battery, could be something that you plug in the wall. There's an associated E with that, and that E is sometimes called the electromotive force. And it's in volts, which is why the term force is a little unfortunate. But the point is that this is a thing that's pushing charges uphill, right? So it's providing some extra energy such that that energy can then afterwards be thrown away as heat in the resistor or as light in the LED. So there you go. That's your R. That's the resistor. And then this, not to be forgotten, this is an ideal wire. Okay, what do we mean by ideal? No R. In other words, no matter how big the current that you run through these wires, there's no voltage drop. Now, so for any realistic material at room temperature, that's a gross simplification, but there are actual materials where this happens, and those materials are known as superconductors. And sadly, we haven't figured out how to make superconductors that work at room temperature yet, but we are on the case. Okay, so those are the essential building blocks of DC circuit. So we got power supplies, we got resistors. Those resistors might actually be lamps or bulbs or motors or something, but they will take some energy and it will convert it into either work or heat or something. And this balancing of potential increases and potential decreases is the thing that's going to do the work. All right, now something about color conventions, because this is something that always comes up. I like when I'm wiring these things up, I like to use red wires for anything that's on this side, and then green wires for anything that's on this side. or black wires, doesn't matter. But anyway, one color on this side, one color on that side. So it's clear that this potential at this point is equal to the potential at this point because there's no resistor in between. When we're starting to look at more difficult circuits, you'll see that that color convention can no longer hold. Okay. Now, before we start to do a little bit more complicated more complicated circuits, I want to show you how a measurement of something like this occurs. Well, what we do is right here we insert a current meter, and right here we insert a voltage meter, and that's what we would do, for instance, in a lab. So instead of going this way, go like this through what is also known as an ammeter. So don't take this path. And then at the same time, there is a voltmeter that you connect here. And this voltmeter measures the voltage between this point and that point. And therefore, because it's connected with an ideal wire to this potential, so it's measuring the voltage between the incoming port of the resistor and the outgoing port of the resistor. So voltmeter, ammeter. Okay, so that's the last two. I'm really running out of space. So we have a voltmeter, and it has R to infinity. So in other words, when we connect it here, there's no current that goes through it. And then this is the ammeter or current meter. And that means R goes to 0. All right. So simple circuit. All right. Now let's see what happens if we make the circuit a little bit more interesting. So go back to our original resistor, and so now I 1K 100 ohm. Here you go. So now I pulled some resistors from the snap circuits kits. You see, this is a 100 ohm resistor. It's kind of cool. You get 10K, get 1K resistor. This is a 100 ohm resistor, so it already tells you what it is. Now, before, when I was connecting this, I need to make sure that I don't have this backwards. So there you go. That's the light. Now, instead of having the path go from here straight through the light, I have a path first going through the resistor. Now, it might not be super obvious to you what it's doing because the camera is doing too good of a job hiding all the details. But if I bypass the resistor here, you'll see the effect. So this presence of this extra resistor does definitely something. And in fact, if I go from 100 ohm to kits are really cool, but they're a little bit strong. Okay, so you see the light's still on, right? Because it's on, but it's definitely more dim now, right? This is with it bypassed, and this is with it not bypassed. So there's something happening when we force the current to go first through a resistor and then through this light. The light is, in this case, another resistor. So two resistors that need to be traversed in a single continuous circle before the charges are back at this point are therefore something special. So this configuration is called a series configuration. So the series configuration is series series configuration schematically looks very similar to what we had before. So one resistor, that could be the lamp, and then another resistor, and there we go. So didn't really do much. We just added another resistor, but it should be clear from you that whatever happens to the charges here, all the charges that make it through this resistor, once they're at this point, there's no way back unless they go uphill, which we're not allowed. There's no way back to the power supply unless it goes through the second. So therefore, all the charges that go through here are equal to all the charges that go through there. So therefore, the current that goes through here needs to also go through there, because there's nothing here that's holding the charges. There's no, can't store any charges. Later on, we'll talk about things that can store charges. So there is some kind of a current here, and then I'm going to call this R1, and I'm going to call this R2, and then there's a current here, and then there's a current there, and now we're going to ask ourselves, what's the relation between the current and those two resistor values? We have some kind of an E here, and we can call that 3 volts. Doesn't matter. And how do we find the current in this case? Oh, but by the way, something I did not mention. So so I draw resistors like this. I think that's a European thing. And this is, I think, the way. See, I can't even draw it normal. So it's a zigzag line. You see, it's like this zigzag line. I'm not just being stubborn in refusing to draw my resistors as this. This thing, once you start drawing circuits really quickly, this thing will start looking like an inductor. And if you ever mistake an inductor for a resistor, you're going to blow up your circuit, or it will not work. So just bear with me. These are my resistors. Forget about this zigzag line, and please adopt this convention instead. Plus, nice thing is, you have a little space. You can actually put a label in there. You can put an R there, or 1 ohm, or whatever you want. Okay, so off to the side. So how do we find the current? So we actually have everything we need already. We know that if we have a point A here, point B, point C, point D, and a point E, we know that we can draw the same potential diagram. We can start here at point A. We're only going to care about potential differences, so we don't really care what happens. And then we end up in point B. And now my question to you is, and I'm going to do this with Nearpod. Give me a second to set it up. So there's a C, there's a D, and then there's an E, and then we're back in A. Okay, so assume R1 is R2. Draw this. All right. So, well, let's take this stroll through the potential landscape. From A to B, we have the same potential increase that we had before. And now from B to C, nothing happens. So we end up here, B to C. And then from C to D, something happens. And I'm going to draw it. Let me use different colors. So C. So first, we're going to do this. This is not correct, so don't use this yet. Now we're in D. And now from D to E, there's another drop because we go in the direction of the current. And we are now here. And now we are back where we started. So this point is important. We have to be back where we started. So this drop and this drop together must add to this increase because of Kirchhoff's voltage rule. Now, the question is, how big are these drops and how are they related? Well, this would be the voltage drop across resistor number 1. So we're going to call that V1. We're going to call that R1 times I1. I1 is the current that goes through resistor 1. This is going to be V2 is R2 I2. Now in this case, I1 is equal to I2 because whatever current goes through here also must go through here because there's no charges being lost here. There's none being stored here either. So whatever current goes through here is the same as the current goes through there. So this one is equal to that one. And in addition, I said R1 is equal to R2. So in other words, this V1 is equal to V2. So in other words, this drop has to be divided into two equal drops. So this red one was incorrect. It's in fact, it's this one. So there we go. And it's important that you remember that this is the same level. So the other thing is that you have to remember that if you go through these resistors in this direction, it's all downhill. You can't have any potential increases because there's no more batteries. All right. So so in general, if we have this this potential increase, and then we have a potential decrease, because the current is the same for these two, we can actually zoom out a little bit and we can say, you know what we can do? We can actually put this in a box. Put this in a box. And from the outside, once we're back here in this point, once it gets back to this point, there are some current going in and there's some current going out. And from the outside, between this point and this point, all you see current going in, current going out, and there's some kind of a voltage drop. It could be 2 drops, could be 1 drop. But clearly there's this voltage drop and it's related to the total current that runs through because these two currents are the same. So is there a way that we can treat these two resistors as one resistor in one box? And of course, the answer is yes. So we do the same thing here in the circuit diagram. And so we can replace this with a single resistor. And then we can use a single resistor R12. And for R12, it follows that the voltage through that R12 is the voltage drop across the first one, because it first drops here, then it drops there, plus the voltage drop across the second one. And then the current that goes through that composite resistor that we made out of these two resistors is equal to the current that goes through number 1, is equal to the current that goes through number 2. And therefore, because the voltages add and the currents are the same, the resistance, which would be by definition V12 over I12, would be V12, that would be V1 plus V2 over I12. Now I12 is equal to I1, and I12 is also equal to I2, and this is R1, and this is R2. So R12 is R1 plus R2. So if this is, let's call this 1 kilo ohm, and sorry, this is 1 kilo ohm, this is 1 kilo ohm, together they make up 2 kilo ohms. And if you want to know what the total current is, you can treat that as a single resistance resistor, and then you go up by E, whatever that voltage is, and you go down by R, that total resistance, times the current, solve for the current, you get the current, and then you get the voltage drops. So the question that came up is, does this thing always need to start in the up direction? And of course, the answer is no. For instance, there's nothing that prevents you from, if you're particularly masochistic, from going in the opposite direction. So you could go this way, and now you're going through the resistor in a direction that is opposite to the current. So first you get this increase, then another increase, and then you go through the battery in a reverse, and you get a decrease. So in that case, so you get, it looks weird, and that's why I didn't do it, but you know, it doesn't hurt. So we start here in point A, and we go from A to E, and then we go, oops, sorry, I started wrong. A to E, and then we go through resistor R1, resistor R2, and then we go through the battery down. That's if you go backwards. So this would be E, this would be D, this would be C, and then we're back in B and A. Okay, so that's if you go backwards. You can make it even a little bit more funny looking. You can start in point D. There's nothing that says you can't start in point D. So start in point D, and now we're going backwards through point D. We're going up through the resistor in a direction opposite to the current flow. So going up, and then we go through the battery, but we go through the battery in a direction opposite to the polarity of the battery, because this one's bigger than that one. So we go down, but we end up below this potential because we still need to go back up through that last battery to make it back to the point D. So D, and this would be A. So these are exactly the same balanced voltages, except it looks really weird if you do it this way, but there's nothing particularly wrong with it. You might have a bit harder time analyzing the circuit if you were doing it this way. All right, and in fact, we will we will do circuits where this is unavoidable, where we will have to, because of the way that the circuit is laid out, we will have to make little voltage diagrams where we will traverse the circuit some point in a direction opposite to the current. Okay, so for series configuration, this R1 plus R2 is the equivalent resistance of R12. Currents are the same, voltages add. So we can generalize this because if we have, let's say, an R123 of 3 in series, it would be R12 plus an R3, because first we can take the 1 and 2 together and then the 3. And then R12 would be R1 plus R2 plus R3, and the voltages would add as well. So V123 would be the V12 plus V3 is V1 plus V2 plus V3. Now, as proper physicists, we do 1, 2, 3 infinity. So generalize R1 through N is the sum of Ri. And the voltages is the same sum of the voltages. Currents are the same. Okay, so that's generalized series circuit. All right, we didn't close the loop, so as to say, when we were talking about this light, and I said, you know, obviously there's something that happens when you add a resistor to the circuit. So let me remind you what we saw. So we had a resistor. My 100 ohm. So this is with 100 ohm, and if I take this wire and I bypass the resistor, remember to remind me to make sure that I tell you what the path of least resistance is, because it's a terrible phrase. You see that if I bypass this resistor, obviously there is more light. So what's happening here is that the total voltage drop across this circuit is 3 volts. Some of that voltage drops across the resistor, and some of that drops across the LED. Now, if I bypass this with a so-called ideal wire, almost no current runs through this resistor, which means we get the full voltage drop across the LED, and that's why it burns at the full strength. So if instead I do this with a with the 1K resistor. 1K resistor, because it's much bigger resistance, takes a bigger voltage drop. So the voltage that dropped across this resistor is going to be bigger. So therefore, the voltage drop across this LED is smaller. And you see it is really smaller. And in fact, I think if we use a 10K, I don't think you'll see anything anymore. So let me, yeah, see, nothing happens anymore. But thing still works. All right, so that's our series and our parallel configurations. Sorry, our series configurations. Now let's do parallel. So parallel resistors. So the parallel resistors are, when they are in parallel. So I will use this one, and I'm going to use this one, and now it's going to take me a little bit of work, but I will put a 1K and 100 ohm. I'll put them in parallel. And now finally, yes, right, hang on. So this could be, configuration of parallel and series. So I have a 1K resistor, and then in parallel I have the 100 ohm. And you see when I add the 100 ohm, the light goes up. All right, so something's happening when we have a configuration like this that makes the total current that flows through the circuit higher. And we're gonna explore how that works, because you might be tempted that because this resistor is the smallest, that's the 100 ohm resistor, and this is the 1K resistor, the path of least resistance, as the phrase goes, says that all the current should go through the one with the least resistance, except that's not true. Most of the current will go through the one with the least resistance, but not all of it. All right, so let's see how that works in equations. So go like this. We have a we use the one resistor, and then the two resistors. So this is R1, and this is R2, and this is our battery E again. And given a certain battery voltage and some R1 and R2, what's the current? Well, we know, what do we know? We know that the voltage difference between this point and that point is the same as the voltage difference between this point and that point, because, let me draw this, on the red side, these are connected with an ideal wire, so no matter how big the current or even the direction the current runs, there's no voltage difference between these 2 points. So therefore, the drop across R1 is the same as the drop across R2. So we know that V1 is V2. We also know that V1 is equal to V2 is equal to the battery voltage, because this thing is also connected to the battery through ideal wires. All right, so we know that. We know that R1 is V1 over I1, and we know that R2 is V2 over I2. We know that there's there's some current that goes in here. And as soon as we're in this junction here, let's call that junction number A, there are two ways the current can flow. It can go in this direction, and then it becomes the current that goes through I2. So that's an I2. And then the current that can go this way is the current that goes in I1, and the combined current we're going to call I12. So I12 splits in an I1 and an I2. Now the question is, what's the relation between I1 and I2? Now, imagine that you were, a little, some kind of a person that can see the electrons moving, or whatever charged particles are moving, and you count the number of charges moving. The charges cannot accumulate here. This is a node. It doesn't store any charge. So all these charges, some of them will go this way, some of them go this way, but no matter how you phrase it, the total number of incoming charges per unit time must be equal to the total number of outgoing charges, independent of whether they go this way or that way. So that's the way that we're going to relate the current. So we're going to say I12 is I1 plus I2. All right, so this is the conservation of charge in action, right? So we have some kind of a box that we could draw around here if you want, some kind of a Gaussian surface, and the total incoming current is equal to the total outgoing current. Net current is 0 because charge is conserved, right? So incoming is outgoing. So I1 is equal to I12 is equal to I1 plus I2, and now we can use Ohm's law for this circuit to express that. So I1 would be V1 over R1. Oops, plus V2 over R2, and that I12 would be our the current that goes through the resistor that we can form out of these two resistors. That I12 would be the V12 over R12. Now, we know that V1 is equal to V2, and once we replace everything between this point, let's start labeling them. So point A, B, C, and D, anything that we have between A and D, we replace that with a single resistor. That current that goes into that single resistor is going to call I12, and that's going to be this one. And the voltage drop across that resistor will be V12. And V12, therefore, is going to be equal to E, also V1, and also V2. So all these voltages are the same. So in other words, R12 is equal to R1, R2. Done. All right, so what does that look like? Well, we replace this with a single resistor in the middle, and we call this R12. And let's do the voltage diagram. Now in this case, we have two loops. We have a loop that goes from, let's call this P, this goes Q. So we start in P, we go up, then we go through R1, down, back to, so Q, A, and then D, and now we're back in P. That's loop number one. That's loop one that we have if we traverse this in path number one in that direction. Okay, so this is number one. So, loop number one. Now, loop number two is over here. There's actually, you could also make a loop number two like this if you want, but let's not do that. Loop number two, we could say is here. So I'm gonna say, go this way. Number two, all right, we start in, well, it doesn't really matter where we start. But we could start in point A. So start in point A, we're going to go clockwise. So we're going to go from A through R2. We're going in the direction of the current, sorry, from A through R2 in the direction of the current. So we're here. So going down, B, C, and now we're in C. And now point D. And now we're going, because we're following this loop, we're going through R1, but we're going in a direction that is opposite to the current. So we're going up. And we are back in point A again. And these levels line up. They line up here as well because of the Kirchhoff's voltage law. And this is the drop from B to C. So that's the drop V2. And this is the increase V1. And this is E, and this is V1. So there are two distinct loops that you can draw. But if you want, you can solve this problem also with one loop going completely in the outer and one loop going in the inner. And we will do circuits that cannot be decomposed in parallel or series configurations. We will do that on Thursday. But for now, let's keep it like this. So now, what is the path of least resistance, right? So there's this phrase: current chooses path of the least resistance. All right, so it's not correct. So I'm going to say that's not correct. So don't, you know. But what does that mean in this context? Well, the current, let's say current 1, it if you wanted to express that as a ratio of, you know, current 1 over current 2, for instance, or you want to say current 1 over the total current, or current 1 over current 2. Now, current 1 over current 2, current 2 is current 1, 2 minus current 1. Okay, current 1 is V1 over R1, and this is V12 over R12, and this is V1 over R1. We can factor out the V's because they're all the same. So it's 1 over R1, 1 over R12, minus 1 over R1, and 1 over R12 minus 1 over R1 is, of course, the 1 over R12 minus R1 over R1 is 1 over R2, right? So it's 1 over R1 over 1 over R2. So in other words, this ratio is inversely proportional to this resistance ratio, right? Because you divide it. So current does not choose the path of least resistance. It favors the path of lower resistance, right? So if I1 is smaller than if R1 is smaller than R2, then this number is going to be bigger than 1. So then this number is bigger than 1, so therefore I1 is going to be bigger than I2, right? So if R1 is bigger than R2, that would do the opposite. Then I2 would be greater than I1. So you see that they go in opposite directions, right? So bigger resistance, smaller current. Now, finally, it's not true, but this is what the real expression says. All right. Now, finally, we haven't. There's one thing that I haven't discussed yet, and that is what happens if you have more than one battery, just for completeness sake. So series configuration of batteries. Of batteries. Well, so you can make that into a single battery by just adding the voltages, because whatever is inside this box you can replace with another thing in the box, and the total voltage increase here is going to be the voltage of this single one. So if this is an E1 and this is an E2, then this is an E12. So our E12 is going to be E1 plus E2. And whatever current that goes through here must be equal to the current that goes through the total. So I12 is I1 is I2. Parallel configuration of batteries. So this is a little trickier because there are certain things you're not supposed to do. So there's an E1 here, and there's an E12. Now you want to be super careful. Usually you will want these to be matched pairs in practice because these things are connected with ideal wires. So if their voltages are not the same, they're going to start discharging each other through each other, and it's just a waste of energy. So, but usually in this configuration, you would have E1 is equal to E2, either because you have charged them exactly equal, or they will get there just through whatever internal resistive losses occur in the battery or in whatever power supply is. But the nice thing is that the currents will add. So the current that gets sourced from this gets added to this I12. So therefore your I12 is equal to I1 plus I2. Okay, so now we have, in principle, all of the building blocks to do more interesting circuit diagrams. So let's do a somewhat more interesting circuit diagram. 5. So combinations of series and parallel. All right, so I'm going to give, put one battery here, another battery here. All right, here we go. This is the diagram. I'm going to make life a little easy. I'm going to give this let's call this 5 volts, and call this 5 volts, and let's make this 1 ohm, and then yeah, let me make the numbers work out nicely. Two, and 2 ohms. All right, so I'm going to call this R1. I'm going to call this R2, R3, R4, R5, and R6. So we're going to work on this this diagram a little bit, but first I want you to tell me what is the relation between R1 and R6. So are they in parallel or in series? And there you go. So I'm going to give you the code. All right. Well, we got a little over 50% of people that correctly identified this as a series configuration. Now, why is it a series configuration and not a parallel configuration? Well, the first thing you need to remember is that just because things are drawn in parallel or are drawn in series doesn't mean that they are in parallel or are in series. So for instance, these are in parallel, not because I drew them in parallel, but because they share not the same current. The current splits up. There's a one current path that goes through here and the other path goes through there. And the current that goes through here is not the same as the current through there. Whereas for a, where's my other one? I dropped my figure 2. There you go. For this one, they're in series because whatever current goes through R1 necessarily needs to go through R2. So, for instance, I could have redrawn this diagram like this. So I just moved this one to the top branch and this one to the bottom branch. Doesn't change anything about the potentials, right? Because there's still an ideal piece of wire that connects these two. There's a piece of wire with a battery that connects these two. So in terms of what the charge carriers are doing, this circuit is identical to this circuit. Or put it another way, you know, if it's electrons, the electrons don't care about gravity. I mean, they do, but it's very, very small effect. So the fact that they are oriented in parallel in this case doesn't mean that they are in parallel. They are in series because the thing to look for is what is the current doing. So the current that goes through number 1 is equal to the current through number 2, and therefore it is a series configuration. So here we go, back to the circuit. So R1 and R6 are in series, but they are not the only resistor that is in series. There's another resistor in series, and that is the resistor that is sitting between, let me point, A, B, C, and D. So that is the resistor that sits between point B and C. And the resistor that sits between point B and C consists of 4 resistors that are doing something really sort of in between series and parallel. So first of all, follow the current. So there's a path that goes from B to C through R2. And that's one way for the current that goes into that junction at point B to go. So it can decide to go down this branch, or it can decide to go through this branch. But then if it goes through here, it also needs to go through there and then through there. And because these are all the same current, and every charge that goes through number 3 needs to go through number 4, needs to go through number 5, these are all in series. And these in series are in parallel with this one. And this configuration is in series with these two. So now let's complete the table. So we have we've got numbers. We have, let me see, 1, 2, 3, 4, 5, 6. Why did I make it so complicated? Okay, number. All right. This is 1, 2, 3, 4, 5, 6. So we're going to call R, and then V, and then I. And then we're going to try to see if we can complete this table. So first things first, we have a series combination of R1, 6, and whatever is in here. So that is 1 through 6. We don't know yet what that is going to be, but we do know that it's made of some kind of a resistor that is composed of 2, 3, 4, 5. So that's 2 through 5, for which we have to determine a resistor. And then 2, 3, 4, 5, we have to use 3, 4, 5 in parallel with 2 to get that. All right. So 3 through 5 is easy. So 3 through 5 is 1, 2, 3 resistors of 2 ohms. So that's 6 ohms. And this one is 6 ohms. And of course, it's not an accident. This 6 ohms is in parallel with this 6 ohms. So the parallel configuration is going to be 1 over 6 plus 1 over 6. And then add to that, it's going to give you 2 over 6. That's 1/3. Reverse it, that's 3. So this one is 3 ohms. All right, now it's 3 ohms from here to there. So therefore, from here through 1, 3, 1, not through this one, but through whatever the effect is, it's going to give you 1, 3, 1. It's going to give you 5 ohms. All right, so now we are done because that is the total resistance of the circuit. That's the resistance between points A and D. In other words, that is the resistance that's going to consume all of this voltage drop, and therefore we can solve for the current. So here we go. So if it's 5 ohms, and we know that the total voltage is going to be 5 plus 5 is 10 volts, then the current through Ohm's law is going to be 2 amps. All right, now we know that it's 2 amps, which means this is 2 amps. This current flows through number 1, through number 6, and it also flows through this total thing. So it goes through number, what did I say? Number 1 and number 6. So that's 2, and that's 2. And we know those resistances, those are 1 and 1. Sorry, those are 1 and 1. So therefore, the voltage is R times I. So that's going to be 2 volts. 2 volts. All right. And now the last 2 amps. Yes. Okay. So now I have this current, that's 2 amp, and this current is going to go through this branch. So that means that it's, let me see, that's 2, 3, 4, 5. That's 2 through 5. That current is also 2 amps. So therefore, if it's 2 amps, and it is 3 ohms, that means this is 6 volts, right? Because V is R times I. Now this voltage that drops from here to there is the same as the voltage that drops across this. So that's number 2, so that's 6 volts. And it's also equal to this that drops across this one. So 6 volts, we know that's a 6 ohm resistor. So that's going to give you 1 amp. So there's 1 amp that goes this way. So 2 amps, 1 amp, and then the other is also 1 amp because 6 and 6 gives you 1 amp. And now that's 1 amp that flows through this, this, and this. So that gives you 1 amp, 1 amp, 1 amp. And those resistors are 2, 2, and 2. Sorry. I don't know why I started trying at 3. So voltage is 2 volts, 2 volts, 2 volts. So which adds up to 6, which works. All right. This is how you solve circuits like this. So you first work your way out, and then you work your way in, filling in the blanks, using Ohm's law to go back and forth. and using the parallel and series configurations to figure out which one of these to populate. So now finally, we can draw a diagram. We can go from D to A. I'm going to draw this in 10 volts right away. And I would go through R1, and R1 has a voltage drop as 2 volts. So 2 volts. And now we are in point B. And now we go from B to C. We do 6 volts. So that's 6 volts. And then from C to D, that last 2 volt drop. And then we're back in D. So that's loop number 1. In this direction. We can also do this loop. All right, so let's start in point C. We're going to go point C. We're going to go from point C through this resistor. We're going in the direction opposite to the current. So we're going to go up to the tune of whatever the voltage drop across 2 is. So that's 6 volts. So we're going to go up by 6. So 6 volts. We end up in point B. And then we go back in 3 steps, equal steps, 1, 2, 3, down here again. So 1, 2, 3, done. So that's, I didn't ascribe points, but you get it. That's 2 volts, 2 volts, 2 volts. So these are the two distinct circuit loops that you can draw. Again, it doesn't need to be the only one. You can also do a loop like this and a loop like that. But when we have series and parallel configurations, we can totally do this. All right. Now, all right, last one. I'm going to give you a riddle. So I'm going to draw a diagram, and I'm going to make it quite complicated. All right, here we go. So they're all 1 ohm, and they're all 1 volt. So all the resistors are 1 ohm, and they're all the batteries are 1 volt. And I'd like to know what this current is. Let me give you one hint. So we want to know the current through here, which means we need to know the voltage. Well, all these are at the same voltage because they're all connected with ideal wires. And I'm stopping this whenever I'm hitting some kind of a circuit element. And then the voltage difference between there and there, which means I need to know it down to here. So these are all at the same potential. I'll give you a minute more. So yeah, the big surprise with this circuit is that there's this one specific path that you could take through the circuit where there's a very clearly defined potential difference between here and there if you go through this battery. Because no matter what the other batteries and resistors do, these are connected with ideal wires. Some of these batteries might be really unhappy because they might be driven in reverse, and they might start to smoke. But we're assuming a perfect battery. So this thing, no matter come high or what is the hell or high water or something, this thing is going to see the same voltage difference as this battery. So in other words, if this is 1 volt and this is 1 ohm, that's 1 amp. So there you go. It's 1 amp. All right, let me bring back my camera so you can see my face again. All right, so that's our introduction to circuits. I've jumped over a whole bunch of stuff. So for instance, we always assume that in circuit theory that I is dq dt, and that for simplicity's sake, we're saying that Q are positive charges that are following the direction of the current. Now, that's not strictly necessary. So for instance, in metals, the current is actually carried by electrons. So the electrons would go in the opposite direction, but if they're negative charges, they're going in that direction, you can see that as a net charge of positive charges going in that direction. And the negative charges go in opposite directions through batteries, then they would get the opposite voltage as well. So and then through resistors, they would dump their energy in the same way. Anyway, if you keep track of where all the charges, if you keep track of where all the signs are, that's everything should work out. But for simplicity's sake, we're always assuming that it's that they're positively charged particles. But for instance, in my lab, I do experiments where I make a tiny little nanopore that is 2 nanometers or 3 nanometers in size, and then I immerse the whole thing in salt water, and then I drive KCl through it. And then my current is actually carried by 2 types of charges, K pluses that go this way with the current, and the Cl minus that go in that direction with the current. And then if we feeling like it, we actually send DNA through as well, and DNA is negatively charged, we follow the Cl minuses, and that would also constitute a current. And in fact, in electrophysiology, this is all you do, and this is of course how our central nervous system works. So circuit theory is not only useful for describing things with resistors and lamps. It also describes how our nerves work, how you feel when something goes from here to there, how when you see something, once the signal is on the retina, how it gets transported to the brain. So the charge carriers might be different, and there might be other funky molecular things happening, but still fundamentally it's a circuit theory problem. So I hope you realize that this can go quite a way. And for instance, the thing that pumps the heart, there's a little signal that basically forces the heart muscle to contract. That's also an electrical signal. You can actually pick that up, and that's what an electrocardiogram does. So circuits are all around. We are made of circuits. So I hope you realize it goes a little bit beyond batteries and LEDs. So with that, hope you like the riddle. I love these things. I find circuits not only because it's the thing I do all the time in my lab. I just find it very satisfying to do a nice little complicated circuit problem, because it's a little bit like a puzzle. So hope you share that enthusiasm with me. And then with that said, for those of you that want to come to office hours, I'll see you in a couple of minutes. Thanks.